everybody. Can you please take your places? Because we will start. For the next talk, I'm excited to introduce Daria Mustafina, who will be sharing her insights on efficient time series forecasting with thousands of local models on Databricks. Daria develops forecasting systems at Eneco, runs creative workshops for kids on weekends, and supports wind energy projects in Ukraine in her free time. A woman of many talents. Thank you so much for being here today. And let's give her a warm welcome and a round of applause.
Yeah, thanks, Julia. Hi, everyone. Thanks for joining today. I'm Daria, Senior Data Scientist at Eneco, the Dutch energy supplier with a focus on renewable energy. Today, I'll talk about scaling time series forecasting, specifically how we go from the one single time series model to thousands local time series model on Databricks, and what choices enable us to scale. I'll focus on the architecture designs, the trade-offs, lessons learned from production, and the practical impact of having the forecasting scalable system. And the core goal of the session is to share our journey in making the scaling forecasting system at our company, and to show you the engine behind the distributed forecasting and how it can be customized for particular business cases. A quick structure for today. I'll start with the business context at Eneco, why forecasting matters at utility companies. Then what multiple time series look like in practice, how we train and forecast at scale, how we do the backtesting of the models in the realistic production-oriented way, and finally our lessons learned and recommendations. Actually, accurate forecasting is fundamental for everything we do at Eneco and every decision we make at Eneco. Because we need to know how much energy we need to buy or sell on the market based on the forecast. Forecasters used to operate wind and solar parks, optimize the battery storage, optimize the smart charging for electrical vehicles, and also for price forecasting. Before, the energy utility companies had an easy job. We needed just total demand for electricity and gas in the Netherlands to forecast it, and it's quite predictable. But now the energy system becomes more decentralized, more electrified, and we have now renewables. People have residential assets like solar or electrical vehicles, and we have big, large assets as solar and wind parks. So today, the forecasting needs to be much more granular, because every time series becomes with its own dynamics. Our time series dataset is quite conceptually simple. We have the group key, the unique series identifiers that makes this single time series as a part of the panel data, timestamp, of course, and the targets. And targets could be multiple: consumption, production, or number of calls to the call center of the company. And optional regressors, additional parameters that can be useful to explain, is weather, holidays, and prices. So the challenge of the forecasting is not in the schema itself, but in the scale. And there are plenty of great libraries like Neural Profit, Darts, skTime, Nixtla. So all these Python, Pandas libraries, great individually, but they don't automatically scale. So the question is, how do we keep using these libraries, but distribute them across the Spark cluster? And the main mechanisms that enabling scaling the Python functions on Spark is Pandas functions on Spark, which is called applying Pandas. So applying Pandas, what it does underneath, so Spark splits the data set into the groups, ships each groups to the Python worker, executes Python model, and then collects the results into our Spark data frame. So we start with the Spark data frame and we end with the Spark data frame with multiple groups, but all the logic is in the Pandas executed in parallel. So applying Pandas is the bridge between Python time series libraries and distributed execution. And if we look at the libraries that exist for multiple time series, then you would see indeed this engine of applying Pandas is used in Databricks menu models forecasting, in Nixla stats forecast. They have a special project to distribute their library and their models. So I'm showing you the engine inside this tool so you can customize it yourself for your business cases, and you don't need to use necessarily the libraries and the library syntax. You can just yourself put the logic into the applying Pandas. Eneco moved to Databricks a couple of years ago, and we now can focus really on the forecasting problems, not the infrastructure. And Databricks has everything we need, so distributed compute, integration with MLflow, Delta Lake, Delta tables, and monitoring and dashboarding. Okay. So let me start with the simplest and most powerful workflow. So we train the model. Immediately generate the forecast, and we don't store any fitted model. So there is no intermediate storage of the artifacts. MLflow still is used for storing the metadata only. This architecture is ideal for the quick development, testing, and in fact, synchronous forecasting is sufficient for most large-scale use cases. So we often don't need to store thousands of models. Another powerful mechanism is another Pandas function on Spark is cogroup. Applying in Pandas gives you one group data frame, but cogroup gives you 2 group data frames per group key. And that enables you the patterns that you can provide separately: training Spark data frame and inference Spark data frame. And you don't need to join them because cogroup will join them internally, and all the Spark Python workers will receive 2 data frames. One other tip is using that they supply the training and inference data set together with hyperparameters specific for each time series. So they have 30,000 groups, and they provide hyperparameters for each group separately. So this was about synchronous training and prediction. And in rare cases, sometimes teams want to use asynchronous training and prediction. It means they train the model, store the fitted model, and then asynchronously load the fitted model and do the inferencing. And for that, we tried 2 approaches, and approach 1 is using MLflow. So the idea is straightforward. We start one parent MLflow run on the driver, and then we provide run ID into the applying Pandas. So then children run of the MLflow started to lock all the models inside each Pandas function. So in the end, you get under one parent MLflow object, you get all the locked models for each of the individual time series. And then at the inference time, you can either use wrapper PyFunc model to load just one model and then receive all the models access. The limitations we faced with this is the MLflow API limit. So it's very hidden. When we started to train thousands of models and log them, we just see that some models were not logged. And we didn't get any error or anything. And then we realized that at some point, the APIs, there were so many API calls at the same time that it just hit the limit and they were not logged. So we consider that this approach can be used for a limited number of time series, for example, 100 or maximum 1,000 in our case. Because of this limit, we decided to try another approach, is to store the fitted model into delta table at the unique catalog as the binary and load it at the inference. So that approach allows to avoid the MLflow limit. And how it works in practice, let me show. So we have the training data, we feed the model, and fitted models are stored in the Spark data frame at Unity catalog. And at the inference time, the inference table is co-grouped and used in applying pandas to do the inferencing. So this is the examples how the model should look like to perform this exercise. So we can train the local model in applying pandas, and then it will be stored as the binary. And at the moment of forecast, it can be loaded and used to make the predictions. So this approach also works, but also for a limited number of time series. It's higher than MLflow. It throws the errors not hidden, but that's not the approach we would also recommend. So this approach can be used also for only when the number of time series is limited. For very large number of groups, we recommend to use synchronous training and prediction if possible. For our models, we use backtesting as the evaluation approach, and backtesting is critical for realistic evaluation of forecasting accuracy. We use time series cross-validation, and first we split our data frame into multiple folds for each group and into a training window and future test window that represents the actual operational forecast. What is very important is the preventing of the data leakage, because we faced that multiple times. Although we are aware of this issue, it still somehow appears in the data. It's very important to use the data that is available on the training moment. For example, in our case, realized weather is already known, but for the future, realized weather is not known, and we need to use the weather forecast that was available at the end of the training set. Otherwise, you would be surprised with how good the results will be for the forecasting. So after we prepare the data, split the folds, we can do the parallel executions. Each group and each fold is independently put into the applying pandas again. So now in parallel, the whole backtesting is done in parallel per group key and per backtesting fold. So what it gives, it provides this parallel execution quite quickly, and train the model, predicts the future window for the test window, and returns the metrics. One of the examples for the electricity consumption forecast is we run 20,000 parallel runs for different customer profiles, different power grid areas, and backtesting faults and models, and where machine learning model showed the relative improvement in the forecast accuracy of 25%. And we were able to run this in 23 minutes. We have another team that runs on serverless, and similar amount they can run in 11 minutes with also hyperparameters. So the time will be depending, of course, on the cluster you are using. And another example of how we applied this framework is the more than 1 million forecast in production. So this was for the making the consumption insights on the weather neutral scenario. So normally what we get from the customers is the last year consumption or production of the energy, which was of course depending on the previous year's weather. And we always need to understand what would be the behavior of the customer if the weather would be not just average weather. And if the customer gives us the mandate, we can share this insight as well with the customer and provide the more accurate estimation of how much the customer needs to pay every month for the energy. Yeah, so here are the key things we learned from scaling forecasting to thousands of local models. First, Pandas on sparse scales extremely well. For local modeling and backtesting, it's a very practical way to distribute Python and Pandas libraries without rewriting everything in SQL or PySpark. Second, this model storage became a bottleneck for us. So we found the solutions only for the limited number of time series. It's either ML flow logging or storing the fitted models in the delta tables. So please use it only if in case you really need absolutely required for your business case. Debugging inside applying Pandas is not possible because it's remote workers. So any print or logging just won't appear. So you need some custom logging or, for example, return the logs as the part of the output from the function. Otherwise, you won't be able to see it. The time series leakage is subtle but dangerous, so you always need to create the guardrails in your code that would prevent you from having the future data leaked into the past. And and I think we would recommend to use this framework. It's adopted by many teams already at Eneco. There was a IKEA talk about the scaling with Metaflow, and soon will be a talk about scaling with Ray. So we see that scaling is one of the problems people face in our ecosystem. So this is one of the approaches to scale the forecasting. Yeah, thank you for your attention. I hope you learn how you can scale the forecasting problems and also learn how to not scale them. Thank you.
Thank you so much, Daria, for your speech. Are there any questions? Yes.
Okay, I hope I'm using it correctly. I have a simple question as a simple customer of energy companies. So what I see as a simple customer that the prices are really volatile, mostly not because of the weather and the prediction, but because of some political fluctuations in our globe. So is it somehow this parameters, or I don't know, this data is used in your models, or you rely only on the weather and I don't know, the current market situation?
Is your question about if we use some more data than weather for price forecasting?
Yeah, like for example, the political fluctuation in the world.
Yeah, so the price forecasting is an important part of course, any utility company. It's predominantly driven by solar production. So you would see prices drop during the day when the solar is active because it's produced a lot and it cannot be used because there is no demand during the day. That's why it's a lot of effort to shift somehow behavior of households and businesses to use more energy in these cheap hours. There are teams that take global trends, policy trends into account to adjust the forecast that is just based on the weather. So you're completely right. I don't know, because I'm not part of this team, how big is this portion of this non-weather related components for the forecast.
So thank you for your talk. I was wondering whether you also considered like another methodology to estimate the usage of customers. Like now you have all millions of individual models for like each connection or something like that. But did you also consider like taking or estimating a pooled model, and you add some dummies for each of the individual EAN codes or something like that, which makes that you don't have to estimate all those millions of models.
Yes,
but it has a trade-off maybe in terms of accuracy. I don't know. That's what I'm asking.
Yeah, actually, one of the examples, it was not for individual connection or smart meter, for example. It was for already customer groups. So we treat customers in the groups and look at the behavior of the groups of the customers.
Okay,
but it becomes still big because we have many customer groups, but then they live in different areas. And then on top of that, we want backtesting. So we need to do that, for example, 20 months backtesting to prove for the business that they need to switch to the new model of the forecasting model. The individual connection is only one example that we have now. Indeed, the case that when we need individually is when we need to do individual recommendation, and each customer has different weather sensitivity, and because different customers have different assets at home and different behavior.
Okay, thank you.
Any other question?
Catch.
I had a question about, at some point you mentioned that you train your model based on measured realized weather and then do testing, forecasting based on forecasted weather. Does that mismatch between your weather data not introduce any systematic errors in your outcome?
Systematic errors because of the weather forecast.
Because of you're basically overtaking any systematic errors of your forecasting methods, of your weather forecasting methods.
Yeah, so weather forecasts, actually we get it from several sources, at least 7. So then the forecast is ensemble, final forecast is ensemble of the forecast based on these different sources of the weather. And in most of the cases for the long-term forecasting, we don't use weather forecasts, we use just average weather. So estimation of what will be approximately the average weather over the last 30 years. Although we see now the radiation in the Netherlands is growing.
Thank you.
Any other question from the audience? Okay, then I will play the audience part for a bit. I have a question about the hybrid modeling. So many talks frame a choice between local and global models, but your framework scales local models from what I've understood. Can local and global components be combined in the same architecture?
Yes, so actually some models, for example, neural profit, they have global seasonality, global trend, local trend. So this architecture can use neural profit as the Python function, so then it will be combination. Or the other way around, you train the global model, get the trends and residuals, you train with applying in pandas to get the individual behavior.
Well, thank you for your talk. I had a question because you just said sometimes you do have to predict on a single customer or single connections, but a single connection might have 2 years of usage data, which is not a lot. How do you train a model on such a small data set, and how do you, is it very accurate?
Yeah, so the data, we need to define the behavior of businesses or the customers, and indeed we normally use actually 2 years of training data. And yeah, so the accuracy of the models differs per customer type. So of course the solar customers would be much more difficult to predict because of the weather uncertainty, but for the non-solar customers it's highly predictable. And we have the 15 minutes data for the customers to predict.
Thank you.
Any other question from the audience? Regarding, and this will be the last question, the lessons that you've learned throughout this project, what was the most unexpected technical challenge when moving from a prototype to production scale forecasting?
Yeah, so I think the issue was not mostly technical, but more on the technical and stakeholder side. The stakeholders really they thought that they need reproducibility and they need to store all the data, all the forecasts and all the models. And it became like really huge and the huge costs and just slowed down the whole process. So it took quite some time to convince them that we have reproducible code, we can store for the last 2 rounds the training data and the metadata of the models, and that would be sufficient to reproduce. And now it's quite sorted.
Any other question from the audience? Last chance. Then thank you so much, Daria, for your talk. We were really happy to have you here. We will take a break now, and I think it will extend into the lunch. So I'll see everybody here again after the lunch break. Thank you so much for attending.
Thank you.